Are your kids around? If they are, you might want to cover their ears for a second. I'm going to say a bad word. Are you ready? Timing closure. I know. I hope your kids didn't have to hear that. I also hope they didn't hear whatever you said after that when you thought of trying to get timing closure on your last design. I've got some good news, though. Your kids may well grow up in a world where timing closure isn't a bad word. A world where we're not slaves to the lockstep march of the clock. A world where we can unchain ourselves from the bounds of hard and fast register boundaries and be free to express our RTL the way it was always intended. Free at last. Sorry, got a little carried away there. Hi, I'm Amelia Dalton, host of Chalk Talk, and I hate timing closure. There. I said it. Today, my guest is Andy Caldwell of Tabula, and we're going to talk about putting an end to the oppressive reign of timing closure terror. Tabula's Spacetime architecture, turns out, besides giving us crazy performance for our high bandwidth designs, also makes timing closure drop dead easy. Your kids can even watch. Before we get started, I want to remind everyone that you can click on that Download Now button below your player. There you can download a free white paper that further expands on this topic. Thank you so much for joining me today, Andy.
Certainly, glad to be here.
So, for a lot of engineers that have done FPGA design, timing closure is one of their biggest nightmares. Isn't that right?
Absolutely. Let's look a little bit at that process. So you run the tools, then you look at the timing report and you say, did I have a problem? The report tells you where the problem occurred, and you have a small number of options to explore to try to fix this. Mostly moving logic around, changing the timing constraints, maybe tweaking a tool parameter or two. Then you go back and you do the whole process again. You run the tools, you examine the timing, you figure out where the timing failed now. This is an iterative process, and you can go round and round. You go around the loop so many times because this is really a hit or miss kind of way of improving timing.
Right.
Most of the time, you're not really improving things. You're just changing where the failure occurred. To make matters worse, anytime you have to make an actual change to the design, say inserting a pipeline stage or changing the logic, you start all over. In the life cycle of design, this can mean hundreds of iterations to close timing.
So, can you explain to me where exactly this comes from? Why do we have this awful iterative process?
Much of it comes from an over-constraint of the problem that happens in traditional timing analysis tools.
Okay.
The designer's actual intent was overall latency and bandwidth of the design. Latency is the amount of time the signal takes to propagate from the inputs all the way through the design to the outputs, and bandwidth is the amount of computation you can do per second.
Right.
That was your actual design specification. Unfortunately, traditional timing analysis tools implement this specification by placing the additional constraint that all the flops align to a clock edge. This significantly over-constrains the problem because every flop-to-flop path must meet that one-cycle clock period.
Right. So what do people usually do to fix this problem?
Well, the first thing people try to do is to balance the delay between one flop and another.
Okay.
You're not really improving the process, though. You're just changing which bucket you've put it in. Much of the time, you've just picked a different spot in the netlist that's going to fail timing.
Okay, I got that, I think.
When you've decided you have to really relax the timing constraint, you look to add a pipelining stage. Then you have the question, where do I put that pipeline stage?
Sure.
This is a big guessing process because you're trying to anticipate how the synthesis, place, and route tools will then optimize your design. Where will the delay go? And finally, once you've decided where to put it, then you have a sometimes tedious RTL editing process. And then you have to go and redo the delay balancing process all over again, or you're not going to see any timing improvement. In fact, sometimes you can guess wrong, and this actually makes the timing worse, even though you actually relax the timing constraint.
So I'm guessing we're here with this Chalk Talk because you're going to show us a better way to improve this, right, Andy?
Absolutely. Stylus uses sequential timing to optimize timing.
Okay, wait, stop a second. Andy, what is sequential timing? I haven't heard of that before.
Sequential timing means optimizing your design for the actual latency and bandwidth constraints, rather than all of the individual flop-to-flop delays that are traditionally used. Instead of defining timing as going from an I/O to a flop, or a flop to flop, we infer the overall sequential timing path. And the sequential path goes from an I/O through the stages of registers to the I/O on the other side, or all the way around a possibly multi-cycle sequential loop.
Okay, I think I understand. And Stylus is Tabula's tool, correct?
That's right. Note that no new information is needed from the user in order to get to these sequential timing paths. Stylus infers them from your RTL and the same timing constraints you provided any other tool.
Great. So, Andy, how do we use that information?
Well, Stylus uses this to both drive timing optimization and provide better feedback to users.
Okay.
Let's look at how that works. Stylus automatically reschedules the flops, providing more time where it's needed, where there's more delay. This preserves functionality, latency, bandwidth, all of the actual aspects of your design constraint.
So, won't this make functional debug more difficult?
It really doesn't. Note that we're rescheduling, not retiming.
Okay.
We're not changing the functionality of any of the registers in your design, we're just moving when they occur.
Ah, okay.
When you look at simulation, the functional signatures are exactly the same.
So, Andy, how will this make our design life easier?
Well, first it shows you not just where the problem occurred, but why the problem occurred. Stylus reports a sequential timing path, which is the timing constraint in your design that won't be met by any amount of delay rebudgeting. This takes you straight to the problem, and you can fix it anywhere along the path, significantly reducing the number of iterations required to close timing.
So, Andy, this looks like the RTL I always start with before I start mucking it up.
It really is. In writing RTL for traditional FPGA tools, the designer is required to be aware of and balance the delay between all stages of registers throughout the entirety of the design process. With Stylus, instead you can just write a big ball of combinational logic that is the clean expression of your functionality and put the registers wherever you'd like to have them without worrying about balancing the delay between those computational stages.
Okay, cool.
Further, if you decide after the fact that you want to go back and change the number of pipelining stages, you no longer have to figure out exactly where in your logic to put it to balance delay. Stick it anywhere you like it that's convenient. The beginning, the middle, the end, doesn't matter. Often this means you can change pipeline stages, which is a single line of RTL, and Stylus automatically reschedules those stages to where they need to go in order to maximize your bandwidth.
Okay, Andy, let's back up a little bit here. It seems like this might affect our overall timing closure process with synthesis and place and route.
Well, it does. It simplifies it. Traditional timing closure on an FPGA, you have kind of two choices. You can either use the synthesis timing feedback, which has the advantage of being a short debug cycle, but the disadvantage of questionable accuracy.
Right.
Or you can go all the way through to the router, which gives you more accurate feedback, but is a really long delay cycle. And further, the further away from your RTL you are when you get the timing feedback, the harder it is to decide what you're supposed to change to improve it.
Yeah, I think all of us are painfully aware of this process. So, how are you changing that?
Timing closure loop with Stylus goes through the placement engine, which provides accurate delay information and timing feedback with a short timing debug cycle.
Okay, wait a second, Andy. So this looks to me like what has always been called physical synthesis, and we've been hearing about that for years. How is this different?
Well, the timing feedback comes from a detail placement, and detail placement in a space-time fabric is much better predictor of final timing.
Okay, that's a lot to wrap my head around, Andy. So you're saying that placement in 3 dimensions makes timing prediction easier and more accurate? Is that right?
It really does. There's 2 reasons for that. The first is you simply have more ways to go around a block edge.
Oh.
Rather than having to go just left or right, you can also go left, right, front, back, or up. There are more timing optimal paths in a 3-dimensional space than there are in a 2-dimensional space.
Okay, I think I got it now.
The other reason is that, looked at sequentially, very few places in design are actually timing critical. There's simply fewer places to fail.
True, okay. So explain to me how this works in your tool flow.
Stylus provides a familiar GUI-based interface to drive synthesis, place, and route based on industry-standard inputs for design specification, Verilog, VHDL, SDC.
Okay, that's a relief, because that looks a lot like what I'm used to.
It really is. Stylus provides a tabbed browser view for managing your design process. At the top, you can select project view, look at a schematic, take the timing debug viewer. Then we have project inputs on the left, followed by this panel, which shows you the stage in the flow where you are, as well as instant access to all of the log files and other feedback that Stylus produces. And then finally, the big window that is the detailed viewer, where you can see correlated information between multiple views of your design.
All right. But Andy, we're here to talk about timing closure. Let's take a look at the timing analysis part of this.
This is the timing debug tab on Stylus.
Okay.
See up here on the left, I have a histogram of the timing state of my design. This is pretty typical for sequentially optimized designs. There's simply fewer timing critical paths than you usually see.
Okay.
On the left, I have the frequency asked for and achieved in each of the clock domains in my design. And then over on the right, a pretty traditional presentation of the timing paths and a breakdown of where the delay in each of those paths come from. But keep in mind, these are sequential timing paths. They may be multiple stages of logic long. We're abstracting all the way back to the actual design constraint that can't be met.
Okay.
This takes you straight to the problem. So you can select any one of them, and you see a breakdown of the delay along that path, as well as a direct link back to the file and line number in RTL where this piece of the computation came from.
Ah, all right.
We can also take any of those paths and look at, say, a schematic view of them, which provides a great visual input about the overall nature of the path. This one, for example, is a loop.
Okay, so this sounds similar to what I already do. I don't have to mess with my RTL as much in the beginning, and I'm likely to run into fewer problems and fewer issues when I'm ready to close timing.
Yep. Stylus significantly simplifies the timing closure process by doing away with the iterative, tedious process of delay balancing between registers, and makes adding pipeline stages or other latency changes very trivial.
Great.
Significantly improving developer productivity and shrinking the timing closure loop.
Well, I think that's all I have time for today. Thank you so much for joining me today, Andy. It was a pleasure speaking with you.
You're welcome.
And before we go, don't forget to click that Download Now button below the player to download a free white paper that further expands on this topic. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.